Boston, Massachusetts, USA. Doctors here are making sci-fi dreams come true. They're growing living human body tissue in this laboratory. They're trying to find a way to grow spare body parts for surgery, starting with the basic building blocks of life, cells. And it works. They've already used a process called tissue engineering to make a human ear.
With tissue engineering, we do exactly what its name implies, engineer new tissue.
But it doesn't stop with body tissue. They're engineering whole body organs too.
The more I learn about tissue engineering, the only limiting factor is your imagination. Any organ you can dream of that might be able to be improved, very possibly can be improved.
For Vanessa Joseph and her son Samuel, it means new hope. Samuel was born with only one ear.
I think in the future, you will have the potential to replace any organ that's been damaged by disease.
Samuel was born with a handicap called microtia. It affects about 1 in 6,000 babies.
At the beginning, I felt very, 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 very bad. But right now, I'm pretty good. I'm all right with it. And I can say I'm grateful for him. I don't know what he thinks right now, but he realized that he only has 1 ear. Because when he's looking at a mirror, he pointed out and just tell you, say, Mommy. You know, right now I said I don't have any answer for him. But pretty soon, the answer is coming.
This could be the answer. When he's a little older, doctors hope an implant will stimulate Samuel's own body to grow the missing ear. The implant will be a trigger for a completely natural process. Every one of us is made out of cells. Some cells stay with us all our lives, but most wear out, get damaged, or need to change as we grow. By the time he's 10, some of Samuel's body cells will have been replaced 30 times already. It takes about 50 million cells to make a human being, but they're not all the same. They can only be seen under a microscope. Speeded up hundreds of times, these are nerve cells growing. These cells form the lining of a blood capillary. Skin cells must take the full wear and tear of everyday life, so they regrow very fast. So fast that our whole skin replaces itself every 4 weeks. Muscle cells convert energy from food into movement. When the cells of the heart muscle stop beating, we die. A human life is not one thing. It's what happens when 50 million cells live, work, and die together. Each cell has its own special role. Different groups of cells have different tools to do their work, making them look different. But they all share the same basic form. Most cells look something like this computer simulation. A membrane holds the cell together. Inside, there's a liquid called cytoplasm that lets chemicals move between the different parts. The cell parts are called organelles. Some act like chemical factories, turning nutrients into other chemicals which the body needs. Other parts are structural. They give the cell shape and strength. Inside most cells is a large organelle called the nucleus. It uses the chemical code of DNA to store the recipe for every cell in the body. Every few months, Vanessa takes Samuel for a checkup with ear surgeon Dr. Evie. This time, they're joined by tissue engineer Dr. Charles Vacanti.
Sam, you can have your lollipop now. All done.
Looking inside Sam's right ear, there's nothing wrong. And on his left side, the inner ear looks normal too. It's only the outer ear that he's missing.
Sam.
Surgeons have tackled this problem before.
Almost done.
One of the techniques that would be available to fix the ear when Samuel is about 6 would be to take some ribs from here and carve them up and shape them like an ear, and then to implant them here under the skin.
It's a fix, but repairing injured tissue never looks quite right.
What they've done for decades is repair injured tissue by sewing pieces of what remains together and hoping that it heals. When you use living tissue, such as a piece of rib, and you carve it, it never really has the three-dimensional appearance of an ear. It looks kind of like an ear, but it's still relatively flat. And what we would like to do with tissue engineering is to replace missing parts with living tissue that resembles the tissue that was lost.
Samuel's ear will begin as a bunch of fibers. Adding this chemical makes the fibers mesh together.
Anytime you build something, you start with a design or a template. So in our laboratories, we use a template in the shape of the body part we want to make.
In just a few minutes, the fibers have formed a template for an ear. These fibers will form a framework around which living cells can grow. But there's no substitute for the cells themselves. Doctors take a small number of cells from the patient, feed them with nutrients, and keep them warm in a laboratory incubator. Dripped onto the template, they will start to take hold and grow. Under the microscope, the role of the fibers becomes clear. Slowly, the cells will fill in the gaps between them and turn the template into solid tissue. It takes about 12 weeks. The ear is becoming a living thing, but not capable of living on its own. It must be kept warm and, once every few hours, fed with all the nutrients which it would naturally receive from blood.
What we do with tissue engineering is to take a very, very small piece from the ear and isolate some of those cells. When we put those cells into an incubator, they will multiply. So we can start with one cell and let it divide to 2 cells and then become ultimately 100 cells and 1,000,000 cells.
This is mitosis, the natural process by which cells copy themselves to grow new tissue, seen through a microscope and speeded up 2,000 times. Look closer still at a single cell, and it's clear mitosis is a very organized process. The action centers on the cell's nucleus, where the DNA is stored as strands called chromosomes. The chromosomes curl up and tuck themselves away once their job is done. A lot goes on when a cell divides, so it's easier to watch mitosis in a computer simulation than trying to make sense of microscope images. Here are the chromosomes made from DNA. Before a cell divides, the chromosomes copy themselves duplicating the DNA. Then, as the chromosomes move towards the middle of the nucleus, from the ends of the cell, strands of protein reach inward. The membrane around the nucleus breaks down, the chromosome pairs line up at the center, and the protein fibers attach to them. Suddenly the fibers contract, and the chromosome pairs are split. Two exact copies of the original DNA line up at either end of the cell. Finally, the cell membrane splits, and mitosis has created two identical cells from one original. Tissue engineers hope that the organs they create will one day grow up with their patients.
In theory, if you were taking the patient's own cells and growing them into the shape of an ear, perhaps that ear would grow. And so when the baby's only a few weeks old, you could put on an ear and hopefully it would just grow up with the child and they'd never ever know that they actually had been missing an ear.
The tricky part will be getting the right kinds of tissue to grow in the right places.
If you were to take a number of cells and inject them or place them within the body, basically they would disperse. If we attach the cells to a template, not only does it keep the cells together, but it also will guide the growth of the new tissue and limit it to certain shape and dimensions. If this was solid, then you wouldn't be able to have nutrients and oxygen diffuse through the system, and then all the cells would die.
Samuel could live without a new ear, but making one will prove that tissue engineering works. And if it does, the way will be open to make things like heart valves that could save critically ill people. But as yet, they're not ready to sew any tissue-engineered organ onto a human patient. First, they must make sure it will be safe. These mice have been specially bred to have no fur and no immune system, so their bodies won't reject the ear tissue.
This mouse was before the procedure, and then over here we have a mouse several weeks after the procedure. You can see that it is now forming tissue in the shape of the human ear, and then after a certain number of weeks, the scaffolding that we started with dissolves. So this part will disappear and only the normal living tissue will remain. When it comes to actually doing it in a child, we would take this mold and instead of putting it in a mouse, we would put it under the skin where the ear belongs in the child and have the new ear grow actually in place.
Beyond finding a cure for families affected by microtia, doctors are also starting to understand why it happens in the first place. There's a clue in the fact that sometimes it gets passed down from one generation to the next. It can be linked to a family's genes.
Most parents have never heard of this type of a malformation, and they think they're the only family in the world that has a baby with no ear. In about 10% of families, there are other family members that have this malformation. It might be a sibling, it might be a parent, aunt, uncle, grandparent, but about 10% of the time there's a subtle sense that something was going on in the family.
Yet no one else in Samuel's family has ear problems. Something must have gone wrong when he was growing as a fetus inside his mother's womb. To create all the cells needed for a new baby, mitosis must happen billions of times. It all starts when an egg from the baby's mother fuses with sperm from its father. Both sperm and eggs are very special cells because each holds just half the genetic recipe needed to make a person. Because they're special cells, sperm and eggs are made by a special process. It's called meiosis. First, the DNA is copied so that each chromosome becomes 2 chromatids. The double chromatids line up 2 by 2, one pair from the mother and one pair from the father. Sometimes pieces of DNA cross over between them, making the new DNA unique. Then, rather like mitosis, protein fibers reach in from the ends of the cell as the membrane round the nucleus breaks down. The fibers pull the chromatid pairs apart, and new membranes form around the two cells this creates. These two new cells each contain only half the genetic recipe for a whole person. Meiosis isn't complete until the new cells divide yet again. Once more, a fiber spindle forms to split the chromatids apart. In a man, they all develop into sperm. In a woman, one of them will become an egg. Meiosis only happens to make these special sex cells special because they hold just half the genetic recipe for a whole person.
I've been working on this project about 10 years now. I became involved because I believed that it would help, and that it would help people, and that it would work.
It does work. But like all research involving animals, tissue engineering is controversial.
It would be nearly a painless operation to put on a tissue-engineered ear compared to a very painful operation when one uses ribs.
I think probably the most important thing is it would also be an ear. It would be ear tissue. When you push it and bend it, it's an ear. It's not a stiff rib that's shaped like an ear. So it would basically be indistinguishable as far as the tissue goes from the other ear.
Not to mention when he goes to the beach, there wouldn't be an incision on his chest that people would say, gee, what happened there?
Okay.
If you look at science, nothing is necessary. What you have to weigh is the advantage of the progress to the disadvantage of whatever means you need to attain such progress. If we ever hope to successfully grow a tissue-engineered ear on a child, then I'd say, yes, it's necessary to first demonstrate that it's safe.
His face looked different, but I don't think he really care about that. As long as he has good health, that's enough for me. As long as he can do everything by himself, thanks God for that. That's all.